Okay, so Pradeep, can you just confirm if you see my screen and
Yeah,
you
it
can,
is visible, sir. Visible, sir.
and my voice is fine?
Yes, sir. Fine. Fantastic, sir.
Okay, then we'll start. We are already 5 minutes. We are behind.
Maybe,
Anyway,
sir, people are busy. I think, sir, they
yeah.
did not send actually email. They sent combined email. Yesterday also we had a session, and today
Uh,
also we had a session. I think they should have sent separately probably. That would have been better.
oh, they are separating together, huh?
No, no, no. They have sent the email together. Like first one was yesterday's, then today's was below that. So probably people missed to see that because I also missed to see that. Suddenly I just remember I have to attend the class today. So
Okay.
I think they should probably send separate reminder every week for today or for today your class also and other class also. Yeah.
Okay, I'll remind them. Maybe uh, I don't know how they do that, but
Yeah, it
anyway.
should have been today, sir. Actually, if today it reaches, then people will remember actually in the morning
Hmm.
if it reaches. Yeah. They
Yeah,
sent
yeah.
the email yesterday. Yesterday.
Okay. So anyway, we'll start because whatever happened happened. Uh, yeah. Then see, last time we ended on the Reynolds transport theorem.
Yeah, Reynolds transport theorem, sir. So there is
There.
something called Navier-Stokes equation. Navier-Stokes equation. So when to use that, sir? Navier-Stokes equation, sir. When to use that, and when to use this Reynolds transport theorem, basically for a control value approach for Reynolds transport theorem, sir. But Navier-Stokes, sir, when to use Navier-Stokes equation
Okay.
exactly?
Yeah, actually, we will use it later.
All right.
So
Okay.
Navier-Stokes equation is, I think, nothing but momentum conservation equation. And when you want to study the flow through a pipe or over a plate or somewhere, uh, there you basically go to the Navier-Stokes equation along with the continuity equation and energy
Yes.
conservation equation. But Navier-Stokes equation basically is a momentum conservation equation. So right now we are not uh, diving into the pipe flows and other things, but when we'll go into this laminar flow, pipe flow, that type of that content of the course, there maybe you'll get to see the Navier-Stokes equation. If not, then maybe I'll introduce it later. But for the time being, just keep that thought in your mind. Maybe later we can go back to that.
That's okay.
Okay, so yeah, so as I said, we stopped at the RTT equations.
Yes, sir.
So first is the uh, let's say mm, conservation of mass, or it is called as continuity equation also.
Yes, sir.
So if you can just go back to the notes and 1 second, I'll just open my previous notes. Yeah, so basically, uh, if you put, like, we had this p and beta variables in the Duvernay equations last time we had seen that. So if
So
we just uh, put uh, b equal to the mass of the system, and then your intensive property becomes mass divided mass, which is 1, and that gives you if you put them in the uh, RTT equation using sorry the RTT equation only, you can say, then it becomes dm by dt of your system will be equal to d by dt integral of around control volume rho dv plus this surface forces. It becomes simply rho uh, vr into n cap dA. So basically, in place of beta you put 1, and in place of capital V you put m. And we know that for a system, mass is always conserved, so there is no change of mass with respect to time for a system. So that side becomes 0, and this is your famous continuity equation. But we typically don't use it in this form. Generally, we do some assumptions such as you like depending on like this second integral, which is the inlet outlet across the control volume. What is the flux that is coming in, coming out? That this term captures that phenomena. So it becomes the function of number of inlets or outlets, and this term, which is the volume integral, so it is basically the change of mass of your control volume with respect to time. So typically we write it this fashion. So maybe we'll take some examples because we are already behind the this thing. But before going into that, see, you can simplify this equation uh, because in most of the cases that we deal, uh, we assume that your inlet outlets are having uniform cross-sectional area. So the surface integral essentially reduces to the average velocity across that inlet or outlet. And if your flow is steady, this dm by dt term also goes to 0, because when you say something is steady, that means with respect to time there is no change. So like in that case, let's say, like if you assume uh, for a steady flow, dm by dt of control volume goes to 0, and for average flow velocity across inlet or outlet, uh, if you like if you assume the velocities that are given to you on at the inlet and the outlet are average velocities, then your this surface integral also this 1 second, this vr dot n dA term also essentially uh, boils down to the mm, the surface integral goes away because anyway you are getting the surface average velocities there. So this again becomes simply uh, rho vr into a. Now it depends where you apply it, inlet or outlet. And if your control volume is not deformable and not moving, then this term also, this velocity terms becomes just a velocity. There will be no relative velocity thing there, and then it becomes rho va inlet outlet. Uh, okay, so uh, and we know that mass flow rate is by definition it is given by rho av. V is the velocity, surface average velocity. So therefore, this is the average mass flow rate. So this essentially becomes m dot, and now it depends where you want to apply this, inlet or outlet. So and again there is a this general sign convention that I discussed in last class, that when your area normal aligns with your velocity, then your dot products become positive, and when the angle between them is 180 degrees, it's negative. So therefore, we consider outlet as positive because the outlet velocity and the surface outlet are in the same direction, and generally the mass entering your system is considered as negative sign. This is the sign convention, so nothing major about it. So just to get familiarized with, we'll solve an example. So see, this may look quite trivial to you, but in GATE 2016, this question was asked for 1 mark, I think in mechanical paper. So they have given you a geometry like this. So this is a schematic. Don't look at exact lines and all, because I'm just drawing it here. So there is a fluid flow and it is getting divided into two streams. Here this dimension is 450 mm. This dimension is 300 mm, and the second stream dimension is 200 mm. uh, and it is a rectangular channel, and they have said that there is a unit depth. So the depth into the plane of the paper or plane of the screen here, it will be one unity. So that is okay. Now they have mentioned that the flow rate uh, at the inlet is 9 meter cube per second.
So what did you say, unity?
So like this is the top view of the assembly. There is one inlet and two outlet. So and they are like rectangular cross-sectional pipes. And so ideally, when I say 450 mm width, there should be some height also, right? Since it's a rectangle. But in question, it is mentioned that consider that height as 1 meter or unity. So
Got it.
no need to worry about the dimension that is not visible in this figure. It is assumed to be 1, like that. And they have given that velocity in the this channel velocity is 3 meter per second. And now question is asked, what is the velocity in this channel? So this is a typical question, and this is purely an application of continuity equation. There is no, you know, I mean, you will be surprised when this type of questions are asked in GATE exam, because in GATE exam, even 1 mark is very important. So anyway, coming back to the point, we can solve this assuming very simple control volume. Okay, so just to avoid confusion, we can assume control volume like this, so that the control volume is also perpendicular to the flow direction everywhere. So this is our control volume, red lines, shown by the red lines. So now, yeah, and it is mentioned that the flow is steady. There is nothing like that. Typical water is flowing through it. So they're asking what is the velocity at the outlet. So now, as I said here, uh, since it is a steady state flow, this dm by dt of control volume term goes to 0, the first term on the LHS, and only the last term, which is basically like if you apply, let's say I'll use some from continuity equation. So RHS is equal to 0, and since it's a steady system, the other volume integral also goes to 0. And now look at this control volume shown by red dots or red lines, dashed lines. As I told you, the sign convention that we follow is outlet is considered as positive because it aligns with the outward normal to that surface. So here, what are the outlets? Outlets are in these two channels, 300 mm and 200 mm. So let's say we'll consider the flow rate flowing through this as Q1 and Q2, and let's say we consider as Q3. So these are the variables that we assume. So outlet is positive, so Q1 is positive, Q2 is also positive, but Q3 is the inlet, so we'll consider it as minus. And therefore, we have Q1 plus Q2 equal to Q3. See, you may say that this is very simple question, but see, I can complicate this just by changing the control volume. For example, what I mean is, let's say, instead of taking this control volume, uh, let's say it was like this. So instead of taking this control volume like the earlier one, I can complicate it just by taking it as a rectangle. But then it is not good for our answer, right? Because now we have to take the components of velocity in the direction perpendicular to the control volume surface and etc. So to avoid that complication, what we typically do is we generally take the control volume also perpendicular to the flow direction, so that dot product and all we need not to be worried about. So it will be like this. So yeah, so then the solving is simple. So basically flow rate is nothing but density into mass flow rate. So, and since the same fluid is flowing, we can say it will be m dot 1 plus, or is it the opposite? One second. Mass is mass by volume is density. Okay, huh? So the rho will be at the denominator because volume, density units are kg per meter cube, and then this will be m dot 3 by rho. Since it's the same fluid, it doesn't matter. The rho will get cancelled, and it is incompressible flow. So now, see, it has mentioned like Q3 is directly given. So, uh, you know, we could have kept this thing as Q3 only. There was no need to change it. One second. Yeah, anyway, let's go ahead. So now m dot 1 is again rho A A1 V1 plus rho A2 V2, that will become rho A3 V3. So again this rho gets cancelled. So basically we have A1 V1 plus A2 V2 equal to A3 V3, and now it becomes easy because now this we have V2 is known, and what will be the A1? A1 is nothing but the cross-sectional area of the pipe. So from the figure, is let's say, I mean, this is the one. So A1 is nothing but 300 into uh, like unit depth, right? So okay, this 300 will become 0.3 meter, right? Because we are taking unit depth. V1 is unknown, that is to be found. A2 is again 0.2 into 1 because there is a unit depth. V2 we know it is 3 given in the question. Now in the question directly Q3 is given, which is 9 meter cube per second. So now we don't know A3 V3. We directly know their this thing, product. So area has the unit of meter square, velocity is meter per second, so it is meter cube per second. So basically this 9 meter cube per second is the actual value of A3 V3. We don't know them individually, but that doesn't matter. We don't need them at all. So now if you see, there is one equation, one unknown. So we can solve this. This will become 0.6 equal to 9, and this is 0.3 into V1. So, oh, excuse me, this 9 meter cube per second is actually 0.9 meter cube per second. I made a mistake while writing down the value, but that doesn't change the logic of the question. So this is 0.9, so only this number becomes 0.9, and this number also becomes 0.9. So you can see this gives you V equal to 1 meter per second. So like that. So this is the like simple application of applying uh, continuity equation to the control volume. And see, typically what happens when you solve any problem, like you'll see in the next part, that what happens, this continuity equation generally it is not solved alone. It is solved in in like in tandem or in parallel with the, in combination with the other this thing, uh, force balance, linear momentum balance, and other these equations. So there you will see that this becomes the first step of the problem solving, and secondly comes the force balance. But anyway, since we are discussing this thing, uh, we'll just uh, Sharif, Sharif, do you want to ask anything? Hello. uh, Sharif, are you like? Do you want to ask anything, or just by mistake your mic is unmuted? Because I'm not hearing anything from your side, so that's all. Anyway, the conservation equation is like linear momentum, or uh, they call it force balance also. Uh, so in that case, uh, they typically call it linear momentum conservation equation. So like in the RTT equations, you put P equal to linear momentum, and therefore your beta will be just velocity, and your this RTT it reduces to uh, summation of external unbalanced forces on the RHS, because uh, Newton's second law states that uh, like if there is any unbalanced external force acting on the system, it will it is nothing but equal to the linear momentum of the system. So therefore the RHS, which is the system property, it becomes summation of external forces. And the other terms like the volume integral, uh, it is d by dt, volume integral cv, rho into velocity. This is the first term, and then you have this flux term, which is rho into v into vr dot n cap dA. So again, we can simplify this. Typically in this course, we simplify it and use it for our problem solvings. And then again, same, like if you assume same assumptions as the continuity equation, if you assume steady state or steady control volume, then this volume integral goes, and then only the second term will remain, and that's how it goes. It's like similar to the earlier one. So we'll start with some problems in this case. So there is this class of problems here, like they are typically asked from these sections, is like uh, you know 1 second, let me just confirm this. One second. M1V1. Hmm. 1 second, I'm just looking at some problems. Yeah, we can maybe start with like simple one. 1 second. I have the problem, but I'm not able to find it. It went somewhere. Just give me some time, okay? Hmm. Anyway, this thing is there, like jet impingement. Like typically, like if you know solve linear momentum conservation, uh, like there are some typical classes of problems that you'll face. So one is like impinging, jet impingement. So there also you use mostly linear, like continuity equation and linear conservation equation, linear momentum conservation equation. So I was just looking into that. uh, so yeah, I'll take one problem. This was very interesting problem. It is, I think, also previous year gate question. So let's say this is question number 2. There is a horizontal plate, or like one plate is there which is lying on the ground, like that. Let's say I'll draw a plate like this, and what is happening is uh, there is one jet of fluid which is impinging on this plate, like here. The flow rate is q0, it is given in the question, and then the this fluid stream gets divided into two streams, and it flows like this. It is given that like 1/4 of the fluid goes the this direction, and then there is this angle of impingement which is called as theta. uh, so we need to find theta. So what is theta? That is the question, and this much, that's it. Nothing else, no other information is given. So see, here also you apply the let's say first of all, uh, from see, if you see any problem where you think uh, we don't have much to go on, first thing that you can do is just go and apply the continuity equation. That is usually a good starting point. You will get some sort of information out of it. So now there is and let's say we take this plate area. You can take the whole plate also, it doesn't matter, because anyway this inlet and outlet are the same only. So if we take this as a control volume, it is a stationary control volume because the plate is not moving or anything. So for this control volume, again it is a steady state equilibrium, like the plate is in stationary state, so there is no time change like of any property with respect to time. So again it will reduce to something like this, whatever is like q1 plus q2 equal to q3. So let's call this q1, and the outlet, second outlet, is q2, which is unknown. So from continuity equation, uh, and since nothing is mentioned in the question, you can assume that the cross sectional area are same. But whether we need that information or not, that is another part. But since nothing else is given, you can go ahead. So from continuity equation, it is clear that q0 will be q1 plus q2, right? And q1 is nothing but q0 by 4. Therefore q2 is 3 by 4 times q0, or maybe 0.75 times q0. So this much we know. Now uh, no other information was given. It is just told that the plate is uh, in a stationary state. It is not moving or anything because of this fluid impingement. So in that case, now one can think of uh, linear momentum conservation, because uh, in this system there is no movement, no linear movement, no angular movement. So linear momentum will be conserved, and angular momentum will also be conserved. So if you think here, let's say we are applying linear momentum conservation equation. Uh, So now what are the external forces acting on this system? That is the question, right? But before going into that, we know that momentum is a vector quantity, and here you cannot directly apply it because the forces are not in the same line. Their line of action is different. Q0 is at angle theta to the vertical and other two are horizontal. So like intuitively it should come to your mind that the important direction is tangential direction to the plate, right? Because you can take the component of Q0 vertically and horizontally, but the vertical force component will be balanced by the normal reaction from the ground. But the tangential force, since there is no movement, the forces will be balanced by each other. The force interactions in the horizontal direction, or maybe I'll just simplify, uh, like just resolve the forces first. We'll apply the
So
conservation.
one thing, how did you know that you have to apply linear conservation equation here? Like, what is the
Yeah,
clue that?
yeah, yeah. So yeah, I think it is better I explain it properly. So see, this is your ground, okay? 1 second. So this is the ground or maybe plate, whatever you want to call it. And you have one force coming in this direction, right? At let's say some angle theta. So this when the fluid is coming and hitting the plate, its momentum is, you know, it has some momentum initially, but when it hits the plate, its momentum is getting reduced, and therefore there will be some force. So the the fluid will exert some force in that direction on the plate, right? Uh, but this force can be resolved into two components, right? One can be the vertical component and one can be the horizontal component. So let's say this vertical component is acting like this. So this vertical component will be it will get balanced by the normal reaction from the ground, right, or the plate. Normal reaction from plate, because there is no any other force acting in the vertical direction. There is one force which is because of the fluid jet, and then there will be the reaction force as per the Newton's third law. So these two forces will get balanced. Let's say I call okay, so if I call this as N and the vertical force by the fluid as Fy, then since the system is in equilibrium, uh, summation of forces in y direction will be zero, right? Otherwise system won't be in equilibrium, and therefore this Fy will be equal to the normal reaction. But does that solve our question? We need to find theta, right? There is like we can't do anything about it now. So therefore now we should look at the horizontal direction force balance. So in horizontal direction you have one force like this coming from the fluid, like this force you can take it on the control volume, and then there is one fluid stream which is going out like this, so it will have some momentum, and one fluid stream which is coming in the opposite direction, so it will be like this. So now if you consider summation of forces in x direction, it should also be equal to 0 because system is in equilibrium in x and y both direction. So now what all the forces are acting in the x direction? That is the question, because y direction force balance did not help us. We wanted to find theta and it did not give much information. But let's say now we apply this applying linear momentum conservation equation in x direction. So then your equation will become summation of forces in x direction, and it is a steady system, so that volume integral term will go, and only the cross sectional area term will be remaining. This cross sectional area rho V dot in cap into dA. And again, these flow rates that are given here are the volume or the surface area averaged flow rate. So this integral, this surface integral also goes. So essentially, what will remain is m dot, because m dot is rho AV. So one rho, this A and V, and there will be one velocity term which is remaining. In mass conservation, only m dot remained in the end, but here m dot V will remain because it is the momentum equation per unit time. So in that case, now and yeah, like you need to apply it at inlet or outlet, whatever you, according to your problem, you change that. Understood? So now m dot is nothing but rho AV, and it is like, I mean, you can write this as rho QV, since m dot, which is mass flow rate, is nothing but the density into volume flow rate. I am changing it because in this question volume flow rates are given. Otherwise, you can take mass flow rates also depending on the given data in the question. So now the net force in the x direction is 0 because the system is in equilibrium. Now in the control volume that we have chosen, the plate, what are the outlet m dot v, like this m dot v inlet outlet term is there, right? So outlet will be considered as positive. So and since rho is also same, it is water, so rho qv, instead of that we can just write qv. So qv, and let's say we consider q2 first. One second now. Okay, so now we first, let's take q2 into v2 plus q1 is also going out of the control volume, so q1 v1 and minus q0, let's say v0. Let's say that it is coming with the velocity v0. So now the question is, what do we know about like these things, v2, v1 and v0? So now we are again stuck here, so we don't know about the velocities, right? So let me just check the question if any other thing is given here. Yeah, the other data that is given is the plate is smooth. So like it was mentioned, the plate is smooth. So what it means is there is like the loss in the velocity because of the friction is 0. You can assume it as negligible. So in mathematics term, you can assume it as 0. So that gives you the one more hint that v0 and v1 and v2 all will be same. We'll call it as some constant v. This is like when you'll study this hydraulic machines, in that chapter there is this very important term is there, smooth plate. What does it mean? So whenever fluid is flowing on some curved surface or flat surface, when they say it is a smooth surface, that implies that the velocity, uh, or maybe you can assume the coefficient of friction very small on that surface, and therefore there will be no velocity change. The velocity will remain constant when flowing through that surface. So now it solves our like problem further, but I forgot one thing. See, this q1 and q2, they are in the x direction, but q0 is not in the x direction, right? So we need to take the component of q0 v0 in the x direction. So that will be q0 v0 into sine theta. Just look at the figure, and from trigonometry you will see the vertical component will be cos theta and the horizontal component will be the sine theta. So now finally somewhere the theta is appearing in our equation. So let's hope that we'll get some idea about this. So since the plate is smooth, the v1, v0, v2 are v, and therefore they get cancelled from the both the sides. Therefore we have q2 plus q1 minus q0 into sine theta. Therefore sine theta is, if you rearrange the terms, it becomes q2 plus q1 . One second. Okay. Did I do mistake again? There is one negative sign coming up. One second. Yeah. There should be a negative sign, because let me draw the control volume properly. Let's say I'll draw it here. Only the x direction I'll draw. So what is happening in our control volume is Q2 is going out here, Q1 is going out from here, and there is one Q0 sine theta component that is coming in from here. One second. And one V is going out here and the other V is going like this. Actually, because of this, see what I told you earlier, right? In mass conservation, whatever is going out, you take it positive. Whatever is coming in, you take it negative. But since this is a momentum conservation, now you need to look at the momentum directions. So like, let's say simple thing, if we take, let's consider momentum in this direction as positive and momentum in this direction as negative, then the Q2 will be positive and Q0 will be the positive momentum, and the negative side you have Q1. So if you balance them, then it becomes, one second, sine theta becomes Q1 minus Q2 by Q0. Okay. One second. I think this is correct. Sine theta becomes Q1 minus Q2 by Q0. So Q1 is 1 by 4. Q2 is 0.75. So minus 0.5 it becomes. So sine theta of minus 0.5 is minus 30. Yeah, so like, coming back to what we did here, so there is one mistake that I did in the sign convention in this step. See, that is actually very important. So see, this is the force balance, right? So when you say net forces acting in the x direction are 0, maybe that is why I did the mistake, because there are no net external forces. When the external forces are there, you need to you can't just go with this sign convention that we followed for the control volume in the continuity equation, because continuity is nothing but a mass balance, right? And mass is a scalar. So scalar, the direction doesn't matter, but in case of forces, the direction matters. So when we say we are doing m dot v at inlet or outlet, we need to take one sign convention, and like typically the right words is positive and left words is negative. One second, this is wrong. So the sign convention that we are following is forces, like in this direction x-axis is positive, in this direction of x-axis is negative. So therefore like this LHS is 0, there is no problem there because system is in equilibrium. But the x direction forces, which are so there will be this q2 here, q1 is the negative. So q2 and q0 are in the same direction, so therefore they are considered as positive. So q2 into v2 will be there, plus q0 into sine theta into v0. These two are positive forces, and then we have negative direction q1 v1, and since they are all, the velocities are all same, there will be change here also. And it will become okay, q2 minus q1 plus q0 sin theta. Therefore sin theta will be q1 minus q2 by q0. So q1 was 0.25 times q0 minus 0.75 times q0. This 0.7 we got from the continuity equation. So therefore the sin theta comes minus 0.5. So therefore theta is 30 degree. You can't take it minus, right? Because I mean, like the sign convention, because of the sign convention, minus 0.5 has come. So practically speaking, you should put modulus sign here, so that will avoid your confusion. So mod of 0.5 is 0.5, minus 0.5 is 0.5, so theta is 30. So like this was like one of the toughest question in that year. I remember many of the people did not solve because this is not a typical question that comes. Typical question that comes is basically, I'll tell you what is the typical question. Let's say yeah, so maybe we should have started with some easy question, but I thought we'll go with the difficult one. So again, this was asked in one of the GATE paper. So there is a tank like this. The height between the free surface and the like midpoint of the jet, like one jet is flowing out of here like this, and it is hitting a wall. So on wall it is spreading like this. Yeah, something like this. And there is a rigid wall. This is your rigid wall. And it is asked that the diameter, this is a circular jet, and the diameter is 300 mm. And the typical question, like what is asked is, what is the net horizontal force experienced by the rigid wall, and it is given that take G as 10 meter per second square, and and one more assumption is that the water level, the 6.2 meter water level, it is not changing because the hole at the bottom is very small, and therefore the level you can assume it as a constant 6.2 meter, like for the like longer time. This is the typical question that is asked. So maybe I should have started with this. I started with this, and somewhere down the line I only got confused. Anyway, applying continuity actually continuity we don't need here. You know, one second, I think, see, this velocity we need, right? Okay, continuity we don't need because there is no like multiple inlet outlet. So do you know one thing? Let us say, I mean, like if you would have done Bernoulli's theorem or Bernoulli's equation, then I could have directly written it. But let's say there is a small mass here.
We have already done Bernoulli's.
Yeah, but I have not told you till now, right? So
Yes.
I'll just try to explain that V equal to under root 2G at how it comes. So let's consider one small mass here. So if you consider this as your height 0, so this will be your height, let's say capital H. So when this mass flows through this small opening at the bottom, you can apply, like, you can see, right, its potential energy, which was mgh, gets fully converted into the kinetic energy, which is m half mv square. Let's say v is the velocity at the bottom. Therefore v becomes, this mass gets cancelled, v becomes under root 2gh, because we will use that here to solve this question. I just gave you this example of small mass. You may get confused, but since I have not, gone through the Bernoulli equation, which is the conservation of mechanical energy, for the time being, you can understand that the velocity that is coming out of the bottom hole is under root 2gh, and this is valid only if the h, capital H, is constant, which is true for this question. It was given in the question. So now, therefore, directly you can apply linear momentum conservation equation. So now you need to take control volume, first step. So you can take this system as the control volume, and so what happens, your fluid, I'll show it by red color, it applies force on the wall, and since wall is rigid, it cannot move. It will apply normal reaction force as per the Newton's second law. So this is the external force. Since it is in external x direction, I'll call it Fx. That is acting on your control volume. There is no other force acting on it, right? This is your reaction force. And therefore, the linear momentum conservation simplifies as f of x will be this thing. What are the momentum terms in the x direction? There is only one which is coming in, right? So like this red jet you are seeing, right? In x direction only you see. In y direction, half is going up and half is going down, so that balances each other. But in x direction, your some mass flow rate is coming and its velocity is v at the start, but finally it is reducing to zero in x direction. It can be non-zero in y direction, but since we are applying linear momentum conservation equation in x direction, so only x direction velocities and momentum you have to consider. Therefore, like this v becoming zero, but actually there is some velocity to the fluid still remaining, and that is the y direction velocity, but we are not considering y direction equation. Therefore, fx becomes m dot is nothing but rho a v, and here v, so it is rho a v square, and now it is water, so it will be 1000. Area will be pi by 4 d square. It is 0.3 meter square, so 0.3 square into velocity. Velocity was under root 2 gh. So in question it is given that take g as 10 and h as 6.2 meters. So if you do this calculation, you should get 8.76 kilonewton. And trust me, this looks like easy question, but it was asked for 2 marks, and the difficult one which we discussed earlier, it was only 1 mark question. So anyway, this is the typical fashion that is followed. I can take one more question from this. Actually, see, next week also, I think there is only one problem solving session. 1 second, let me just confirm, because I was seeing through the course this thing. What you call? Yeah. So next week there is all the problem solving things are there. So today I am thinking I'll stick with this conservation equation numericals, and maybe next week, since it's anyway problem solving, we can do Bernoulli equation, which is like momentum energy conservation equation, and some cases of it like flow measurement devices and other things, pitot tube, piezometer, etc. And so that another like some problems from earlier classes that we could not do because of the time constraint. I think one chapter was the submerged body part, fluid statics of submerged bodies, that we did not take many examples earlier. Maybe we can go back there and revisit. So therefore today I am more or less focusing on these RTT type of questions. I can take some in between if you want, but this linear and all will take next time. Linear, sorry, Bernoulli and all. So 1 second. Yeah, there is one more variation in this type of questions. 1 second, let me just check. Sorry. So dimensional is there. Pipe flow is there. I'm just checking the syllabus, so that I should not do something which is to be covered later. That is only my question. Laminar boundary layer, buoyancy, drag and lift is there. Okay, so we can take this question, or maybe I like question you can solve, but I'll just tell you what happens. Okay, so in some cases, what happens? The plate that you are considering, it may not be stationary, it may be moving. That happens typically in turbines. There is something called as like when you study hydro machinery or turbo machinery, there are important classes of work producing devices which are turbines, and there are classifications of them. Amongst them, there is one category of turbine which is called as Pelton wheel turbine, which was preliminary turbine that was invented. That was like the first working turbine that was invented by humankind. Nowadays, it's not that used because it has certain drawbacks. Nowadays, better alternatives are there. Francis turbine, Kaplan turbine, all are there. But in Pelton wheel, what like in any wheel, if you say if you are hitting a wheel tangentially with some water stream, the wheel will rotate, right, and that is what creates the torque at the wheel shaft, and that is you feed it to a dynamometer and you get the electricity. So in that case, like in this question, the wall was rigid, right? It was not moving. But let's say if I put any turbine at the end, the turbine plate can move, right? So therefore, there is a case where uh, fluid jet uh, strikes a moving flat plate. This is I am taking flat plate just to start the discussion. Uh, the plate can also not be a flat plate; it can be a curved surface also. We'll take one example of that also. Don't worry. Uh, so yeah. So in that case, what happens? There will be, let's say, there is a plate like this, and it is. I am telling you all this because this falls under the category of linear momentum conservation equations, and therefore we are taking this. So it is moving with velocity u, and there is a uh, you know this thing. Uh, there is a jet, fluid jet, which is moving with velocity v. Let's say v1. V1 is the inlet, and it hits the plate, and then it goes out in this direction. I am not drawing the full this thing because v2. But again, see, now you should be familiar with the concept of relative velocity, because this v2, it's not actually v2, it should be relative velocity of outlet with respect to the plate. So it will be vr2, and it is like, let's say, smooth plate, so there is no velocity loss. But the actual velocity, if you draw the uh, you know uh, this thing, what you call, uh, velocity triangle at the outlet, relative velocity concept. So it will be like this. So this will be your actual velocity, this is your relative velocity, and this is the velocity of your plate. So in reality, when the plate is moving and the stream is hitting it, the outlet will not be vertical. The outlet stream, it will be looking like it will be at certain angle. So that you need to this thing, you need to understand that. And like, since it's a smooth flow, uh, the total mass flow rate that is coming in, it will be getting divided into two parts, m dot by half of will go up, half of will go down. This is only valid for a smooth plate. If plate is rough, I don't know, then we have to apply continuity equation, and from there you get how much mass is going up and going down. So that is there. And here also at the inlet, what is happening if you draw again, when the fluid jet is hitting the plate, it is hitting it at relative velocity. So, and all these velocities are in one line. So what is happening basically is this total length is your v1, the velocity of the jet, and this is your this thing, velocity of your plate, and you have some relative velocity here. I hope you understand why v1 will be greater than u. Does anybody have doubt that why v1 should be greater than u? Uh, because if v1 is not greater than u, your jet will not reach the plate at all. Your jet should be moving at higher speed than the plate, right? Then only it can hit the plate. If the plate is moving at higher speed than the jet, then jet will never hit the plate. Plate will go, you know, it will go faster and it will never allow jet to hit it. So anyway, so this is the typical setup that we have. So coming back to the the topic that we are discussing. Now here what happens, earlier we used to take mass flow rate as rho a v. Here it will become rho a vr. That is first. And like let's say VR2 here we are taking like that, and it is rho a VR2 and VR, one second, or maybe for like simplicity, instead of VR2 you take VR1 because they are linear, right? If you take VR2 they'll be like under root V2 square plus U2 square. Why to go into that confusion? So it will be V1 minus U. This is your mass flow rate now, which is actually hitting the plate. And what is like from x direction linear momentum conservation equation, we get f of x, the total force that is acting on the moving plate because of the impingement of jet in the x direction will be what was the incoming momentum minus what is the outgoing momentum in the x direction. So in x direction it is m1u, m like half, the stream is getting divided into half, right? And then it is having u velocity. So basically there will be one triangle at the bottom also like this. So this will be your u, this will be your vr2, and this will be your v2. One second. Uh, vr2u. Oh, vr2u2. I should have drawn it properly. So it should look like this, u2, and this will be your v2. Yeah, this is correct. So anyway, the point is a half of mass will be having u velocity at the exit, assuming like plate as the control volume. So therefore, if you do that, you get m dot v1 minus u, and m dot is rho a u. So basically, f of x becomes rho a v v1 minus u square. So this is very important result that you should remember, because like if you consider this problem that we solved here, when there was a rigid wall, your net force was F is equal to rho a v square, because there was no relative velocity or anything like that. But here, since it is moving with relative velocity, uh, there is some loss of the force, and that is because the actual speed at which the fluid hits, it's lesser than the speed which is with which the fluid is moving. So I'm like, this question was asked in the GATE exam. I think this is very old question, but anyway, I'll give you the question details. One second. This will be the fourth question. So same setup. There is a jet coming and hitting a flat plate which is moving at some velocity. So this is a gate question. I'll just give you the values because the diagram is same. There is no change. So V1 was given as 20 meter per second and the plate was moving at 10 meter per second. The cross-sectional area of jet was 0.01 meter square and it is water, so density was 1000. And find what is the total force exerted by the this thing, the jet on the plate. So I mean, like this is like straightforward question, right? So I will leave you with the answer. Maybe we can solve it. It's one step only. So rho A V1 minus U square whole square. So rho is 1000. This is 0.01. V minus U is 10 and it's square, so 100. So it will be 1000. So answer is 1000 Newton. Once you know the formula, it looks very easy, right? Anyway, now the thing is, one second. I'm just checking if any other question is there. Yeah, so mostly gate questions are done. What I want to do is, as I told you earlier, maybe we can take one subjective question. One second. I'm just. It's actually very interesting question, but I am just looking if some easier question can be done in between. That will be better, right? Yeah, one second. I think I found one. Okay. So this is like this is like engineering services question objective. I think prelims they call it. So there is a curved van like this, vane, whatever you want to call. So like the back shape doesn't matter. Forgive my drawing, but it's a smooth plate, and there is this center axis, and there is if you connect it at the back, it's a symmetrical vane. So there is a angle alpha, symmetrical angle alpha, and there is a fluid which is entering at velocity v, which is like smooth entry, and it is leaving smooth also with velocity v. Since it's a smooth plate, there is no velocity drop in between, and it is it is exerting force of like the force exerted on the vane is 100 Newton. Mass flow rate is given as 5 kg per second, and it is water you can assume. And find the vane angle alpha. This is the question. In this case, the plate is stationary. Okay, so maybe I can draw it like this. So it's not moving or anything. It's just a stationary plate. So again, same formula. Fx will be rho a, but here the catch is there, right? Because It's not the flat plate. In flat plate, directly you can write. But here you need to draw free body diagram. So this is your m dot coming in, right? So in x direction it is m dot v. So in x direction, then it will be getting, this is the momentum, right? Momentum term. So there will be m dot v, and let's say which one will be the alpha now. Mm, 1 second. Oh, okay. I should draw it properly. This this is the alpha. Like at what velocity the fluid is entering, that is the angle alpha. So this is the angle alpha. So yeah, so this is the angle alpha given in the question. So this becomes m dot v cos alpha, right? And this is m dot v sin alpha. This is at the inlet, and at the outlet, what is happening? Again, outlet momentum is like this, m dot v, and this angle is alpha. So this will become m dot v cos alpha and m dot v sin alpha. So now it is mentioned that this force exerted on the vane in the x direction, is 100 newtons. So now what you need to do, apply linear momentum conservation equation. So Fx, it becomes, if you consider let's say this direction as positive and this as negative, then what happens, in the positive direction you have at the inlet m dot v cos alpha, minus at the outlet you have same quantity but it will have negative sign, right? Because its direction is in the negative direction. This term I am saying, you should consider it as negative because it is changing the direction. It is going in the negative x direction. So therefore, this becomes 2 m dot v cos alpha, and therefore fx is 100. M dot was given as 5. Uh, v v was also given as 20 meter per second. So 20 into cos alpha. So this becomes 200. So this becomes cos alpha is 1 by 2. Therefore alpha is, I think, 60 degrees Celsius. 60 degrees, not degrees Celsius. Let me just confirm the answer. I think it's 60 only. Yeah. Okay. So we'll take one subjective question after this, and then we'll stop. Maybe next class we'll start with Bernoulli and some remaining problems from earlier. I think in this RTT, this angular momentum conservation is not like it is there in the syllabus, but it's not like in primary, like introductory classes. It's not like focus is not given on that. I'll just check if any. Yeah, mostly it is continuity equation and linear force balance, and then directly Bernoulli. Yeah. Okay. So anyway, it is 7:30. So we'll take one subjective question. Interesting question I came across. That will like conclude today's class. So just bear with me for some time. I will write the question. Maybe if you are watching it online or somewhere, you can stop the video here and try to solve this. This is a subjective question. If you solve it, I think it will be better. Anyway, I'll write this question. Show that maximum efficiency for a jet striking at the center of a single symmetrical vein which is moving with velocity u is given by 16/27 cos square theta by 2, where theta is the vein angle. So this was question asked in the Engineering Services 2014 mechanical subjective paper. I mean, like, this is like the most difficult question as far as the competitive exam concerned, based on maybe linear momentum conservation part you can consider. There can be others, but I found this as a very beautiful question because it will check like all of your understanding about this. So see, it's the same figure. Here it was alpha. In this question, it is mentioned that it is uh, theta, but in this question, the vein was stationary. Now, what is mentioned in this problem is the vein that you considered earlier, which was somewhat like this, symmetrical. Pardon my drawing, but it's a symmetrical, smooth vein. And let this be its center line. Yeah, it should look like smooth, so maybe you can consider it like that. And yeah, so this is your inlet, and maybe this is your outlet. So this is the theta, but now this plate itself is moving with velocity u, with same velocity in x direction as u, and the jet that is coming is like, okay, maybe I'll use different color. So the jet is coming in this direction, and it is getting, okay, yeah, so this is center hitting and going out like this, the same angle theta. Okay, maybe my drawing is not that good, but it should be like that only. Okay, yeah, so this is the jet speed. Now see, don't worry, okay, because see, I took the problems in that sequence only. So here it was stationary plate or stationary rigid wall, then we make the wall move in with some constant velocity u. Similarly, initially here it was a curved vein, and then we made it move with some velocity u. So whatever we did in the moving flat plate case, we have to do the same thing. So what is the thing? The mass flow rate will reduce by the like mass flow rate here it was rho a v1 minus u, right? So here also mass flow rate will become rho a v minus u, correct? Because it's a relative speed. Then the fx that was coming here, it was rho a v minus vu whole square. But here all the forces were in the x direction. But in this case, there is a slight change because now we have angle theta and all. So you can go back and see this case, right? Here also it was theta. So essentially in the end what we got was, first term was, like if I write, this is from continuity equation. And from linear momentum equation, we get the external force as okay. So now the question is, what is coming? So incoming is m dot into v minus u. Okay, and then once it hits the plate, again the sign convention is this direction we are considering positive, this direction we are considering negative, minus what is going out, maybe I can draw it here like this is your relative velocity, which is nothing but v minus u. One second. This thing you can see, right? So you had relative velocity, right? Which is v minus u at the outlet. And since this is a smooth plate, v1, v2 are same. So here it is becoming like this. So one second, I'll just write it. So VR2 will be v minus u at the outlet, this case. And for this case, it is like this, na? Outlet is like this. Again, it is also VR2 because it is a smooth plate and it will be relatively this thing, relative direction. So like that, this is your curve vein. Don't worry if you are not understanding this, what is VR2 and all. Our objective as far as this class is concerned, it is to understand how to apply linear momentum equation. Other things you will learn later in some hydro or fluid machinery course, so don't worry about that. But I just thought I'll introduce you to this concept because it is basically only linear momentum conservation and mass conservation. So here, what like half of the mass flow rate will go in the one direction, which will be v minus u into cos. Now again, so this was your theta, right? So it will become cos theta, but with the minus sign because it is in the negative direction. Here also it will be minus m dot 2 into v minus u into cos theta, because it is coming, half is going out from the top, half is going out from the bottom. So like that. Here also it will be theta. So we are only considering x direction. I'll put here x direction. So therefore it becomes m dot v minus u plus m dot v minus u cos theta. So further if you write it, it becomes m dot v minus u 1 plus cos theta. Okay. Now the question is, you know, talking about the efficiency. So efficiency you may not knowing, but typically what is the efficiency? Efficiency is for how much, like if you put x input, how much output you are getting. If you are getting 0.6 times of the output, 0.6 times of the input, that means your efficiency is 60%. If you are getting 30%, so you will only get 30% of the input as your output. Like that only, for this also it is defined that way. So efficiency is nothing but what you say, work done by jet on vane divided by kinetic energy supplied by the jet, right? So jet was coming with some kinetic energy and it is hitting the plate and plate is producing some work. So that is what efficiency is called as. So again, now we know what is work done. Work is nothing but force into displacement. Now you may ask me why you are taking u, why you are not taking v minus u. It is because the work done is by the vane, and vane is moving with the velocity u. So even if the force has v minus u term in it, the final work done will be always with velocity u. There you can't put some v minus u because it's not a relative thing. Whatever force is coming onto the vane and vane is getting displaced with the velocity u. So basically this all things is per second. Okay. Uh, Maybe you should not get confused by the units. Therefore I am putting it out there. So numerator is also per unit time and denominator is also per unit time. And what is the kinetic energy coming with the jet? Half m dot v square. This is kinetic energy coming with the jet. So we'll put the terms here. Okay. So it will be m dot v minus u cos theta plus 1 divided by half m dot v square. This will be into u because there is one u term is there. Now you need to put m dot value also, which is rho a v minus u. Oh, actually I should not. Yeah, okay. Anyway, so rho a v minus u. One second, guys. Half kinetic energy supplied by per second half mv square m dot rho a u. Oh, okay, okay. Yeah, so this will become your m dot is rho a v minus u. So rho a v minus u whole square 1 plus cos theta. So this is fine. But the kinetic energy that is supplied by the uh, jet, I cannot write it half m dot v square because again m dot is considering relative mass, right? How much mass is hitting the jet vane, but that is not correct, right? Because you are giving this v velocity to the whole mass, which is rho a v. So it should be half. One second. So here it will be rho a u v minus u square and this thing, that is fine. But here it will be half capital M v square. And capital M, what is capital M? Rho a into v square. I hope you are understanding that why I am not taking small m dot here, because uh, see, small m dot is what is hitting the plate, but there is some mass which did not hit the plate, and that is because the plate is moving. And but see, when you are giving the input, you don't consider the mass that is not going to hit the plate, right? You give the v velocity to the whole mass. So therefore I am considering capital M dot, which is rho a v. So that is there. So if you further simplify, the half goes up, rho a get cancelled, it becomes v minus u square into u into 1 plus cos theta divided by v cube. I hope everybody is with me. We'll stop in some time.
But sir, here for the first time, you are using capital M.
Yeah,
And
yeah, yeah. Because see, in this case, here also we did not talk about efficiency, right? See, you understand this way. See, when you are in this case, this is actually a Pelton wheel. This problem is nothing but a Pelton wheel. Only there is one. Guys, 1 second. Somebody's at the door. Uh,
Okay, the others are done. Okay,
Yeah, hello. Sorry, there was some emergency. So yeah, coming back to your question, see, uh, when you are like providing kinetic energy to the inlet stream, you don't know, right, how much of it is going to hit the blade or the vane, and how much is not going to hit it, right? For example, if I, let's say, uh, I provided half m dot v square energy to the stream initially, out of which only half m dot v square is reaching the vane. Okay, this half capital M dot minus small m dot v square, it never reached the vane because your vane is not stationary, right? If the if the vane is stationary or plate is stationary, the full mass will go there and hit it. But since the plate itself is moving with some velocity, uh, the complete mass doesn't go. So this is your waste. Your energy is wasted, waste of kinetic energy. Now what happens? This small m dot reaches to the plate, and out of that, the plate converts Fx into U into the final output, final work output. Okay, but you cannot say that the input energy that I gave to this system was half small m dot v square. No, you gave half capital M dot v square, right? And this term did not come previously because we did not consider work done. We stopped all questions at force. So for force balance, you need small m dot. But if you want to do work done calculation and other further efficiency, etc., you need to consider capital M dot. Maybe right now you may not understand it fully. Maybe when you study some hydro.
it is clear. It is clear.
Yeah. Yeah. So anyway, I'll keep this as a note. Maybe you can refer it later. We'll finish the question and we'll stop. So now the question is, this is our efficiency expression. Now in question it is asking that show that the maximum efficiency that can be obtained uh, with this with like with this theta angle vane, symmetrical vane, is this 16 by 27 cos square theta by 2. So now see, in all of this formula for efficiency, v is the velocity at which this thing, your stream is coming in, so that is fixed. Theta is also fixed because uh, once you make the blade, you can't change theta. The only variable that is in your hand is small u, which is the speed of the vane. So therefore you need to take derivative with respect to du and equate it to 0. That will give you this is like maths. For any governing any y equal to f of x, if you do differentiation of f of x and equate it to 0, the x that it gives is the x at which you get the maximum f of x, the first linear this thing, first differential equation, not differential equation, the solution by differential equation, that optima kind of thing. So if you do this to this efficiency expression, see, 1 plus cos theta remains as it is because it's not a function of u. Then v cube also remains as it is. 2 also remains as it is. The inner part, it will have some changes because there will be chain rule now. So one term will be v minus u square as it is, and u will be differentiated. In another term, it will be u into 2 into v minus u into minus 1. I am assuming everybody knows the chain rule, and therefore this will be equal to 0. Therefore, it will become again 2 into 1 plus cos theta divided by capital V cube into, I'll expand the bracket, v square plus u square minus 2uv, and here it will become minus 2uv plus 2u square equal to 0. Yeah, so basically, see, this term anyway will go to that side and get 0 only. This is v square minus 4uv plus 3u square equal to 0. And if you solve it, it will be v minus 3, 1 second, v minus 3u into v minus u equal to 0. So therefore, v can be equal to u or v can be equal to 3u. So there are two options that uh, this thing, what you say, v can be equal to 0 or v can be 3, v can be equal to 3u. But can anybody tell me one of this choice is not practical? Can anybody tell me? Pradeep, tell me what happens if
v is equal to u is not practical, I think.
Yeah, because when v is equal to u, there is no relative velocity, right? There is no work done.
Yes.
So
Yes.
this is zero work done condition.
Yeah.
But we want maximum work done output, right? So therefore, v equal to 3u. So now this we need to put in the efficiency formula, and that will be maximum efficiency. And if you put it, see, this is the formula, right? V equal to 3u. So what it will become? 2 into v minus u whole square. So v minus u, it will be 2u whole square into u into 1 plus cos theta divided by v cube, right? So v cube will be 27 u cube. Therefore, it will become 4 into 2, 8 u, u cube will get cancelled, 1 plus cos theta divided by 27. And if you apply that cos 2 theta cos theta property, it will become 16 by 27 cos square theta by 2. Since 1 plus cos theta is equal to 2 cos square theta by 2. Okay, and this is what it was asked in the question. Okay, so I mean, this was very interesting question that I came across when I was also preparing for exams. Because if you solve such questions, it will clarify all the concepts that you learn in particular chapter. So that is why I strictly speaking, there is no need for me to take any subjective question in this discussion, because we have been told that if you take previous year questions, objective questions, that should be sufficient. But I don't like that way, because see, the earlier objective, like small questions that we took, they were only asking for fx. They were not going beyond that. But in this case, you had to look into what is the work done, what is the actual energy put into, then you have to differentiate, and then you have to get the maximum efficiency. So this clarifies most of the things that are generally left untouched when you do the objective questions only. So you should sometimes do subjective questions also. That helps. Anyway, so I think we can stop here. Maybe tomorrow, like next Tuesday, since anyway it is problem solving session. We'll do some Bernoulli equation problems, and maybe some problems that we cannot, like we could not do before in previous lectures. So should we stop? Anybody? Somebody said thank you. Thank you to you also.
Thank you, sir.
Sharif, thank you. Okay, then shall we close today's discussion?
Yes, sir.
I'll see you next Tuesday.
Thank you, sir.
Okay.
Good night.
Okay. Bye bye. Take care. Good night.